In this video, we're going to look at inverses of matrices. And when I say inverse, what we're talking about is the multiplicative inverse. So if we think about the multiplicative inverse of a number, that means what do you multiply it with in order to get 1 as your solution? So let's say we had 2, and if we multiplied 2 by its multiplicative inverse, we would end up with 1. So what do you need to multiply 2 with in order to get 1? Well, it's 1/2. We could go a little bit further if we wanted to. We could say, okay, let's say we have 3. What would you multiply 3 with in order to get 1? And it would be 1/3. So we need to figure out a way how to find that 1 over the matrix, and that's what we're going to be looking at in that video. We also can think about why we would need them in that, let's say we had a matrix equation, matrix A times matrix X equals matrix B. And if we wanted to solve for matrix X, if you thought about algebra, you would go, okay, well, I divide both sides by A, and I'm done, right? But we can't really divide by matrices. So we need to think of another way to show dividing by matrix A, or 1 over matrix A, and that's where the multiplicative inverse comes in. Instead of dividing here, what we would do if we had AX equals B is we would need to multiply it by its inverse. And if you remember from our functions, we use that -1 notation to show the inverse. If you multiply both sides by the inverse, that's how we're going to end up with these equaling 1. So we have matrix X equals the inverse of matrix B, or sorry, the inverse of matrix A times B. And that's how we would solve for matrix X. This is going to come in very handy when we solve systems using matrices. So we need to be able to find an inverse. So just sort of to remind you, an inverse, a multiplicative inverse, times the original is going to yield you 1. So that's why we can cross them out in our equation, because they just equal 1. What's kind of interesting is that this works both ways. If you have A and you times it by its multiplicative inverse, it should also equal 1. Just like 1/2 times 2 and 2 times 1/2 are both going to get you 1. Now we're going to need to look at determinants when we find inverses, so be sure you've looked at the determinant video and are good with those before moving on to the rest of this video. Before we actually find any inverses ourselves, we're just going to start by looking at some matrices and trying to figure out if they are inverses. And remember, to figure out if they're inverses, we know that A inverse times A needs to get us 1. So if we multiply these two matrices with each other and we get 1, then that means they're inverses. Remember, we need to check both ways, though. So let's start out with just the order they're written in. So matrix multiplication, we know we're going to have a 2 by 2 matrix at the end, and we need them to equal the identity matrix, the 1 matrix. So if we go ahead and remember our rules, for A11, this first one, we're going to do row 1, column 1. So we're going to have 1 times -2 plus -1 times -3, which is -2 plus 3, which is 1. Ooh, this is a good sign. Now we have some other entries that we need to take care of. Row 1, column 2 is going to get us 1 times -1 plus -1 times -1, which is -1 plus 1, which is 0. So this is another good thing. See, we're almost to our identity matrix. So we got a couple more to take care of before we can be sure. That one, row 2, column 1. So we will have 3 times -2 plus 2 times -3, which is -6 minus 6, which is -12. So automatically I know that these are not inverses because I'm not getting the identity matrix when I'm multiplying them. Remember that multiplicative identity matrix would look like that for a 2 by 2 matrix. So automatically we say no, they are not inverses. So here's another pair of inverses that we are going to check. Remember, we are going to be multiplying them to see if they are inverses, if they do indeed get us that identity matrix. So I'm going to start out with the order they're written in. 6, 5, -2, -2, times 1, 2.5, -1, -3. We know we're going to have a 2 by 2 matrix in the end, and we'll do our multiplication. So we're going to start out with row 1, column 1. So we have 6 and -5, and that is going to give us 1. I'm not going to write out all my steps. We already did multiplying matrices before. So if you need to review how to do that, go back to that video too. But I want to save some space since we have a lot of multiplying to do. Now we have row 1, column 2. So we're going to have 6 times 2.5, which is 15, and -15, so that gets a 0. This is looking good. And row 2, column 1 is going to get us -2 and +2, so that gets a 0. And we have one last entry to look at, and that would be row 2, column 2. So the first thing we need to do is -2 times 2.5, which is -5. And then we have +6, which gets us 1. So it's starting out to look like these two things are matrices, but remember we also need to make sure that they work the other way too. So to check them, I'm going to change the order. Matrices stay the same, but we're just switching around the order to see if we get the identity matrix that way as well. We know we're going to have a 2 by 2 matrix when we're done. Let's start doing our multiplying. We're going to start out with 6 and 2 times 2.5. So 6 minus 5, that's going to get us 1. That's a good thing. Now we'll do our next one, row 1, column 2. That'll be 5, because 5 times 1 is 5, minus 5, because 2.5 times 2 is 5. So that gets us 0, another good thing. Now row 2, column 1, and that's going to give us -6 and +6, which is 0. And row 2, column 2 gets us -5 and +6, which is 1. So because we got the identity matrix for both of these two things, we can say that yes, they are inverses. So that's what we're looking for. We're going to have to be able to find one of those two matrices. That's what our next step is going to be. Now you know what an inverse is, what it is when you multiply it with what its original one was. And so now let's actually look at some ways to find those inverses. So how do you actually find an inverse? We're only going to look at finding inverses of 2 by 2 matrices. So let's say we have matrix A, and matrix A is A, B, C, D. And we want to find the inverse of matrix A. So how are we going to find the inverse of matrix A? The rule for finding the inverse of matrix A is you take 1 over the determinant of A, which we looked at in that previous video, and you multiply it by what I call the mixed-up matrix. The mixed-up matrix flips D and A, and it makes the other two guys negative. That's all you have to do. Once you multiply that out, you'll be able to find the inverse, because the 1 over the determinant is just a number, and you multiply it by all those terms inside. So this is how to find inverse of a 2 by 2 matrix. We can find inverses of higher order matrices, but we're not going to be doing those by hand. So in this video, I'm only going to be doing matrices that are 2 by 2 and finding the inverses of those. Again, you find 1 over the determinant and you multiply it by the mixed up matrix. So if I refer to the mixed up matrix, that is what I'm referring to. So here's the first 2 by 2 matrix we're going to find the inverse of. Remember, to find the inverse, we need 1 over the determinant times the mixed up matrix, which flops these two and makes these two negative. So let's go ahead and start by finding the determinant. The determinant of this matrix is going to be 2 times 4, which is 8, minus 2 times 5, which is 10, so it's negative 2. So to go about actually finding the inverse now, we are going to do 1 over the determinant, so 1 over negative 2, times the mixed up matrix. So we're going to flip 2 and 4, and these two guys are going to become negative. Now it's just scalar multiplication. We did scalar multiplication a long time ago. I know you might not remember it, but that just means multiply all those terms by that number. So we're going to start out by doing negative 1/2 times 4, and that's going to get us negative 2. Then we're going to do negative 1/2 times negative 5, which just gets us 5/2. And we're going to do negative 1/2 times negative 2, which is 1. And we're going to do negative 1/2 times 2, which is negative 1. So that right there is the inverse of matrix A. Now how could we check to see if it was actually the inverse, if we actually did our work right? Remember that if you find the inverse and you multiply it by that matrix A, it's going to end up with the identity matrix. And it has to work both ways. So if you take matrix A and multiply it by its inverse, it also has to end up with the identity matrix. Since we did a bunch of proving on the last couple of slides, I'm going to save that step for you to prove that I actually did it right. I might have done it wrong. Sometimes I do that. And that's one thing that you're going to have in your back pocket when you're solving these problems and you're being asked to find an inverse, is you know that you can check to see that you actually did it correctly. So here's another 2 by 2 matrix to find the inverse of. Remember, the inverse is 1 over the determinant times the mixed up matrix, where you flip those two and you make the other two guys negative. So for this one, determinant, that's our first step. So we're going to have 6 times negative 1, which is negative 6, minus negative 6. Ooh, negative 6 minus negative 6 is 0. Now, we would have to, at this point, do 1 over 0 times our mixed up matrix, which would be negative 1, 6, negative 1, and positive 6. But what is 1 over 0? Well, it's undefined. It's nothing. You can't divide anything by 0. So in this case, we actually don't have to carry out this step. We do not have an inverse for this matrix, and it's that singular matrix that we talked about in our determinant video. So a singular matrix does not have an inverse. We're done. Now that was no fun because that didn't have an inverse. So we're going to do another one that does have an inverse. Remember that to find the inverse, we do 1 over the determinant times the mixed up matrix. So we're going to start this problem by finding the determinant. That would be negative 1 minus 0, which is negative 1. Ooh, a nice and easy one. So now when we plug that in, we are going to end up with 1 over negative 1 times the mixed up matrix, which would be negative 1 and 1 and negative 4 and 0, because a negative 0 is just still 0. Now to finish this off, we're going to multiply all of the entries in that matrix by 1 over the determinant. 1 over negative 1 is just negative 1. So the first entry is negative 1 times negative 1, which is positive 1. Negative 1 times 0, which is 0. Negative 1 times negative 4, which is positive 4. And negative 1 times 1, which is negative 1. So there we have our inverse. Remember that you could check it. If you wanted to check it, you would do A inverse times A, and then you would do A times the inverse that you found. And both of those you would want to equal the identity matrix. Alright, one last inverse just because these are boatloads of fun. Remember the inverse, 1 over the determinant. Figure if I repeat it enough, you guys might get something out of this. Times the mixed up matrix. So let's do it. Let's find the determinant. we're going to have 1 times 2 minus 3 times 4. So we're going to have 2 minus 12, which is negative 10, and that's our determinant. So now when we put that into our inverse, we're going to have 1 over negative 10 times the mixed up matrix. So we flip those two, and we make these two negative. Alright, so multiplying. We're going to end up with negative 1 over 10 times 2, which is negative 2 over 10. The reason I'm writing it off to the side there is because we know that negative 2 over 10 is actually negative 1/5. So that's how I'm going to write my inverse. Sometimes it's handy to keep it in unsimplified form, but for now I'm just going to simplify them because that's good practice. Now the next one is negative 1/10 times negative 3, which is positive 3/10. Can't simplify that. Then we have negative 1/10 times negative 4, which is 4/10. 4/10 is 2/5. And then we're going to have negative 1/10 times 1, which is just negative 1/10. And that is our inverse. You'll notice that I didn't convert any of these to decimals. To me, it's easier to work with fractions. And I know what we're going to be doing with this inverse later on is multiplying it. And so those fractions are actually going to make it a lot easier to do things with the inverse later on. And again, we can always check if we want to by doing A inverse times A and A times A inverse to see if they both get us the identity matrix. See if we actually did our inverse work correctly. So let's say that you have a 3 by 3 matrix or a 4 by 4 matrix or a 100 by 100 matrix and you want to find the determinant of it. You can find the determinant of it. You can do it by hand if you want to, but it's going to require a lot of brute force. So there are some other methods for finding the determinant, and a lot of those require us to look at our technology. I know that you guys like to go straight to technology, but it's important for us to understand how that technology knows what it's doing. If you have any aspirations to do anything in any computer field, you're going to be the one coding the computer to do the inverse, so you have to know how to find the inverse yourself. So if you are going to find the inverse of a matrix using technology, it depends on the calculator you're using. On my graphing calculator that I hold in my hand, and the one you guys do too, all you have to do is enter matrix A, and then raise it to the -1 exponent, and that's going to get you the inverse. If you're using another online calculator or a different handheld calculator, you might see INV as an option. That's what you're going to want to use to find the inverse. You input matrix A that you had already given it, and it will spit out the inverse for you. A lot of times you're going to get some crazy decimals, and you might want to convert them to fractions so you actually know what's going on. Usually the computers or the computer versions for sure will give it to you in decimal form. If you're using a handheld calculator, sometimes they'll be nice and give it to you in fractional form. But those are the two things that you would look for. Now remember, on our calculators that we have, we can really just put in matrix A and then put the -1 as the exponent, and that will do the inverse for us. So that's what that actually is. It's not anything special. You can find a rule on the calculator, though, that looks like what the computer ones look like, that says INV, and then that'll find the inverse for you. It'll even do all those determinant calculations, but it won't tell you what it is. It'll just use it to find the inverse. So just to do our little recap, because I like to recap, we are finding inverses of matrices, and the inverse means the multiplicative inverse. Because we are looking for something that's going to undo a matrix. We're looking for something that when you multiply it by matrix A, it's going to get us the identity matrix. Just like when we were solving using coefficients, because we can't divide by matrices. So when we find the inverse, that's what we're looking for. You can check to see if things are inverses by actually doing this calculation and remembering that you also need to do it the other way just to double check and make sure that that gets you that identity matrix again. That's how you check that things are inverses. How do you actually find the inverse? Well, remember, we only do it for 2 by 2 matrices by hand, and to do that you do 1 over the determinant times the mixed up matrix. And that's how we would find the inverse by hand. That 1 over determinant just ends up being a number, and you multiply that by all the terms. If you're going to use technology, there's a couple different things you would look for. You could raise your matrix to the negative 1 power, or there might be a rule in your calculator that says INV, and that's how you could get the inverse of your matrix using a calculator. So, we spent a lot of time actually talking about how to find inverses. In the next video in this series, I'm going to look at why we actually did that, what we're going to use the inverse to solve. And it's actually going to be something you're excited about because it'll make something you already know how to do quite a bit easier.